All right, let's take a look at today's lesson. We're going to be looking at our properties of rational functions. Let's first of all remind ourselves what is a rational function. Let's start there. So here we go. So a rational function looks like this. It's like a fraction where P and Q are polynomials. So basically, it's a division of two different polynomials. That's what a rational function is. We will be finding domain today. And so here's a little statement on domain. The domain of the function is the set of all real numbers except for those where the denominator q is 0. So that's kind of our little catch right there. And of course, it's a fraction, so we know that the denominator can't be 0. We've known that for quite some time. But that is our guidelines for finding the domain. It's basically everything, all real numbers, except those for which the denominator is 0. So that's our domain. Let's look at over here. This is just a reminder. We did this last year. If you need to refer to last year's notes, you certainly can. We're going to be needing to do long division. So what I did is I put up a completely worked out problem with long division. A completely worked out problem so that you could take a look at it if you needed to remind yourself. What I would do typically, see that there's this blank right here. There's a big blank. I would normally put plus 0x squared instead of leaving it a blank, but doesn't matter. You don't have to. You can leave it a blank. But we need all of, like the fourth degree, third degree, second degree, first degree, constant. We need them all represented. So there's just an example. When we're looking at let's just kind of go right over here, look at the fraction. So if you're going to divide this, if you would recall, we would put the numerator inside the division little box and the denominator on the outside. This would be called the dividend. We went over those vocabulary words yesterday or a couple of days ago. That's the dividend, and this is the divisor. Just a reminder of the order, if I could spell, divisor. Just a reminder of the order that you would put them in when you divide. Okay, so that's polynomial long division. So let's look more in depth as to what we're going to be working with today. So we're going to be working with domain. We're also going to be working with asymptotes. Horizontal and vertical and slant asymptotes. Let's focus on the horizontal and vertical asymptotes first. These math words, these notations are really calculus based, really talking about calculus. So what is it saying? It's saying that so we're looking at horizontal asymptotes first. For a horizontal asymptote, as x approaches negative infinity or positive infinity, the values of r, okay, these are y values. The y values approach some fixed number L, then the line y equals L is the horizontal asymptote. So let's focus on horizontal asymptotes for just a moment. We'll look at these graphs down here. The graph that has, A and B graphs. All right, so as we're looking at, this is our function r. They're calling the function r. And the function r, the x value is going to infinity. That's what the x value is doing. And so the x value is headed to infinity, and notice that the y values are headed to this L, y equals L. Looking at the graph on letter B, we've got our x values they are headed towards a negative infinity, but the y values are headed towards the y value of L. R is headed to L. So let's make a little note about horizontal asymptotes. So horizontal asymptotes, what is that looking like? That means the x values are headed to positive or negative infinity, and the y values are headed to L. That L that you're seeing right up here. That's an example of L. Okay, so I'm going to pause here for a second. How are we on the horizontal asymptotes? So as the x values are headed to positive or negative infinity, the y values are headed to a y value they're calling L. Okay, so those are horizontal asymptotes. Now let's look at vertical asymptotes. Let's look at those. All right, so for vertical asymptotes, notice that my x value is approaching C from the left or the right. So from here's from the right, it's going this way, from the left, it's going this way. And the y value is approaching positive or negative infinity. So this is a bit of a reversal. This is a bit of a reversal. So for vertical asymptotes, the x values are headed to C, and C is an x value, right? The x values are headed to C. C is an x value. And the y values are headed to positive or negative infinity. So this line right here, if you will, that is our vertical asymptote, and our function, they're calling the function named R, is approaching the vertical asymptote on the left and the right and going up to positive infinity or down to negative infinity. Okay, so I'm going to pause here for just a second. Questions on vertical asymptotes. That's basically looking at it from a graphing point of view. From a graphing point of view. As we look up here on the words, as x approaches some number C, the values, the y values, approach infinity or negative infinity, then the line x equals C is a vertical asymptote. Okay, so that's how it looks. That's how it looks graphically. Okay, questions about how it looks graphically. We're going to go through the steps on finding these things, but I want to make sure we're understanding what the graph would look like. A horizontal versus a vertical asymptote. Okay? All right, so now let's look on the how-to. How do we do that? How do we find that? Okay, so let's look at that. So to find the vertical asymptotes, those actually, to be honest, are the most straightforward ones to find. But I want to put an asterisk here on number 1 because that's really important. Before you even attempt to find anything, you must factor and simplify the rational function. That's like, you have to. You've got to do that. Factor and simplify first. The second thing that we would do is we would set the denominator equal to 0. So this is the second thing that we would do, is we would set the denominator equal to 0. And that's how we would find our vertical asymptote. And we're going to practice that. We're going to find vertical asymptotes in just a moment. I'm going over the how-tos first, and then we'll do that. Okay, so for horizontal or oblique asymptotes, now I'm going to draw a little, I usually, instead of using the word oblique, your textbook likes to use the word oblique. I typically use the word slant asymptote. They're talking about the same thing. It's just two different names for the same thing. An oblique or a slant asymptote. What do we do? Okay, step one, just like in the steps above, step one is critical. You've got to factor and simplify first. Okay, so that's first. Now, on number two, if the degree of the numerator is smaller than the degree of the denominator, my horizontal asymptote is going to be y equals 0. So let me give you a little example. So an example of one like this. So here's an example. Let's say I have, x squared plus 2 over x cubed plus 3x minus 1. Let's say I have something like that. Okay, so we look at the degree. So recall the degree. So this is a degree 2, and that's degree 3. We see that 2 is smaller than 3. So we work with number 2. The degree of the numerator is smaller than the degree of the denominator. Then I'll give you an example of what it might look like. Okay, this isn't this particular, I'm just giving you an example. What would that look like? So basically, I would have an asymptote right here on the x-axis. That is the horizontal asymptote y equals 0. So if the degree of the numerator is smaller than the degree of the denominator, that's where your horizontal asymptote is going to be every single time. It's going to be on the x-axis, and the equation is y equals 0. Okay, so let me pause here for a second. Are we okay? So that's how a problem like number 2 would look, an example. So now let's look at an example of like the type 3, where it says the degree of the numerator is equal to the degree of the denominator. Then y is going to equal the ratio of the leading coefficients. Okay, so let's look at an example that looks like that. All right, so what if we did, let's say, 3x squared plus 1 over 2x squared plus x minus 5. Let's just say we have something like that. Okay, so we're kind of focusing on this. We've got the degree of the numerator is 2, the degree of the denominator is 2. They match. They're the same. They are equal. Therefore, we're going to take the ratio of their coefficients. Those are called leading coefficients because they're the numbers in front of the highest exponent. So then my, this would look like this. Okay, my horizontal asymptote would be y equals 3/2. And if I were going to graph it, it would look something like this. It would basically be a horizontal line at 3/2. So that is an example of the item number 3, where the degree of the numerator is the same as the degree of the denominator. Okay, how are we doing? Okay, number 4, this is another type. What if the degree of the numerator is 1 more, just 1 more than the degree of the denominator? Then, if that's the case, we're going to get slant asymptote. It's a slant asymptote. So let's look at an example of that. So let's say we've got this example. Let's say we've got like 4x cubed plus 1 over 3x squared plus 5x minus 2. Okay, so let's kind of focus to see we've got a 3 here and a 2 there. The 3 is 1 bigger than the 2. 1 bigger, so that means we have a slant asymptote. And that means that it would, let's give you an example. I'm going to go over here. So if I were to work on this, I would put the numerator, 4x cubed plus 1, inside of the division. And then I would put the 3x squared plus 5x minus 2 outside. Now, I totally made that up just out of my brain. That's not a nice rehearsed problem. So we're not going to go through the division, but that's how you would find the slant asymptote, is by doing long division. This is what you would do if the degree was 1 more. So maybe you're wondering, or maybe you're not, maybe you're wondering, well, what if it's more than like 2 or more greater? What's going on there? Okay, so that's super fun. I'll give you an example. And you're going to be so upset that we don't have time to do this. I know you're going to be. This is an example. So let's say we had like 3x to the 5th plus 1 over, oh, I don't know, x cubed plus 5x squared minus 5. Okay, what does that mean? That means there's no horizontal asymptote and there's no slant asymptote. There isn't neither one of those are there. But what would be there? It's called a curvilinear asymptote. Doesn't that sound fun? Wouldn't that be so fun? Oh my gosh, I'll show you a curvilinear. This is like 2 degrees higher. We would have something that kind of looks like a parabola asymptote. Doesn't that seem magical? Yes? No? I'm getting a no. I know that would be so much fun to go through, but we just don't have time. I know you're going to be upset with me. We just don't have time for curvilinear asymptotes. Sorry. We're going to have to stick to vertical, horizontal, and slant. Oh, well. So that means you're probably not going to get any problems like number 5. You're probably not going to get any that have the degree 2 or more, because we're not doing that kind. So, but I needed to explain what it was. What if you see that? What does that mean? That's what it means. Okay. So I want to pause here for just a second. I've gone through the whole details, like specifics page, all the notes of what's going on. How are we? Any questions in general about horizontal, vertical, or slant asymptotes? Okay, so then let's jump into the next slide, which is some examples. Let's do some examples of all of these kind of things that we're doing. So let's start with domain. Okay, so let's remind ourselves back up here. So the domain, remember, is everything except where the denominator is 0. I mean, that's what it is. Everything except where the denominator is 0. So let's take a look at this. All right, so I'm going to take the denominator. Now, of course, well, with domain, we're good. So we're just going to set the denominator equal to 0. I'm going to factor instead. There's several ways to do this, ladies, but I would prefer factoring. So that's the difference of squares. So that means x plus 2 is 0, and x minus 2 is 0. So x is negative 2, and x is 2. Okay, so those 2x values are not allowed. We're not allowed to have them because they cause the denominator to be 0. Now, if you want to write it in set notation, I kind of favor set notation, but I'm not sure which way your book is going to ask, so I'll do both. So if we did set notation, it would be all x such that, you know, that whole weird straight line, such that x cannot equal plus or minus 2. This is how we would write it in set notation. Okay, but I think your textbook really likes interval notation, so let's write it that way also. If we needed to write this domain in interval notation, we would go negative infinity to negative 2, then negative 2 to 2, then 2 to infinity. And that would be interval notation. The interval notation is basically highlighting that we need to leave the negative 2 out and we need to leave the 2 out by putting parentheses there. You know, that basically means not including, right? Parentheses is not including, so we're not including the negative 2 or the 2. Okay. So that's an example with domain. Let's look at the second example. They're wanting us to find the vertical asymptotes. Now, before we find any asymptotes, we have to do step 1 from above. Look at step 1, factor and simplify. We have to do that first. Otherwise, we're going to get in big trouble. We're going to have wrong answers, very possibly. So let's do that. Let's factor first and see if we can simplify. So the numerator, that's the difference of perfect squares, x plus 3, x minus 3. All right, the denominator is a quadratic. Hopefully, I'm sure we can factor like FOIL. So we've got x times x. Let's see, the back sign is negative, so the signs are different. We need to multiply to get 21 and subtract to get 4. That's sounding like a 7 and 3 to me. Does that sound right to y'all? 7 and 3? So we'd have a 7 here and a 3 here. Okay, so now I want you to notice we've got a factor in the numerator and denominator that match. That means that we need to delete them. Now, so they're going to go away. But what happens is when we do that, this creates a hole. This creates a hole in the graph. Okay, the hole in the graph is at x equals 3. Okay, to find the y value of the hole, find the y value of the hole, what we do is we plug the x value into the simplified function. Okay. So when we cross out a factor from top to bottom, numerator, denominator, it creates a hole in the graph at the location where that factor is 0, so at x equals 3. And to find the y value of the hole, we would plug the x value into the simplified function. So let's do that. Let's just finish this process. So I'm going to plug the 3 into the simplified part. So 3 plus 3 over 3 plus 7. So what is that? 6/10. So that means we've got a hole at 3/5. And in the graph, you seriously would just put an open circle there. You would go to that point, 3/5, and just put an open circle there. It's an actual hole. It's a hole in the graph that's represented by that open circle. Now that's going to happen to us next class period. We're going to be graphing next class period. We're kind of easing into graphing by spending time on domain and asymptotes so that we're ready to go into graphing next time. So yes, it's very likely that you will find graphs with holes in them. So this is just a how-to if you have a factor that's deleted or simplified. Okay, let me pause there for a second. How are we doing on how wholes are created and how we find the location of the hole? Are we okay? Yes? Okay. So let's finish our simplified version of this, this rational would be b of x is x plus 3 over x plus 7. I mean, that's the simplified version. So to find the vertical asymptote, we would take the denominator, x plus 7, and set it equal to 0. So x is going to be negative 7. That means that I have a vertical asymptote. I usually abbreviate it as VA, vertical asymptote, at x equals negative 7. And that's what they asked us to find, was a vertical asymptote. We just had extra fun finding a hole also. Okay, how are we with holes and vertical asymptotes? Is everybody okay? All right, last one. Number 3, we've got a couple of examples on number 3. So they're wanting us to find either the horizontal or oblique, which I call slant, asymptote. Okay, so how do we know? Well, we would first factor and simplify, A, look at that denominator, x cubed minus x squared plus 1. I'm not really thinking that's factorable. It's not looking good to me. Does it look good to y'all? No, I don't think so. So we're not going there. We're just gonna look at, so this has got x to the 4th and this is x cubed. The numerator is 1 more than the denominator. That means what? It's a slant. Yeah, we're gonna have to do long division. Yep, all of that fun. Okay, great. So let's do that. So the denominator is out front, the x cubed minus x squared plus 1. Open up the division box. Okay, so I've got 3x to the 4th. And what I like to do is I like to insert holding places for the missing, like I've got x to the 4th. I need a holding place for x cubed, so 0x cubed. Do you have to do that? No.
Is it plus 1 or minus 1?
Plus 1. It's plus. Yes, ma'am, it's plus. Okay, so we're going to insert that 0x cubed just as a place marker. Do you have to do that? No. It just makes your division easier. Minus x squared, and I'm going to insert some more place markers, so plus 0x plus 0, just for my ease. Okay, so let's focus on this. So I need to divide, so I've got this term is the one that's dividing in every time, this first one. I don't divide in any of the other ones, it's always the first one. And I'm going to put a little, this is like scratch work over here. We'll put the scratch work up here. So this is scratch work. So basically what I'm doing is I'm taking 3x to the 4th and I'm dividing it by x cubed. That's basically what I'm doing when I'm dividing. I'm taking 3x to the 4th divided by x cubed. So we simplify that. 3 divided by 1 is 3. And x to the 4th divided by x cubed is x. So this is equal to 3x. Right? That's my scratch work. Now, I'm putting the 3x on top of the one that has the x. Why would I do that? See how I'm lining these up? I keep my, for ease in calculations, I keep my variables lined up. Like the first powers are lined up, the second powers, and so forth. Just makes my life easier. Do you have to do that? No, you don't have to do that. I'm just saying it would make your life easier if you did that. All right, so now we multiply back out. So I do 3x times x cubed is 3x to the 4th. 3x times a negative x squared is negative 3x cubed. 3x times 1 is 3x. Okay, I don't have an x squared, so I'm trying to keep these variables lined up. All the x to the first I get lined up because it makes my life easier. Okay, then I divide, I'm subtracting. Remember, that's just how long division works. You subtract that line from the first. So 3x to the fourth minus 3x to the fourth is nothing. 0x cubed minus a minus 3x cubed is a positive 3x cubed. Negative x squared minus 0 is negative x squared. And if you would prefer to put a plus 0x squared there, you can. You don't have to. You could leave it blank if you wanted to. 0x minus 3x is a negative 3x. And then I bring down the last term, which I didn't really have to because it's 0, but why not? Sounds fun. Okay, so I want to pause for a second. How are we doing on our first go round? So now I'm going to take x cubed into, and I'm gonna, let me just highlight. So I took, the first I took in here, now I'm gonna take in here. So my scratch work is, I've got 3x cubed divided by x cubed, and that's 3. Okay, that's just scratch work. Maybe you can do it in your hand, maybe in your head, maybe you have to write it out, whatever you want. All right, so that's 3. So I've got plus 3. So 3 times x cubed is 3x cubed. 3 times negative x squared is negative 3x squared. 3 times 1 is 3. And again, I'm trying to make sure my variables line up. 3x cubed minus 3x cubed is nothing. Negative x squared minus a minus 3x squared is a positive 2x squared. Negative 3x minus 0 is negative 3x. And 0 minus 3 is negative 3. Now, I want to see if I can keep dividing. I've got 2x squared divided by x cubed. That doesn't come out evenly. I'm done dividing. That doesn't work. It would be the same as, let me just show you a number one to describe what I'm talking about. It would be the same as if I were to take like 3 divided into 2, 4, 6, 8, okay? 3 goes into 24 8 times. 8 times 3 is 24, right? We subtract. 3 goes into 6 2 times. 3 times 2 is 6. Subtract, bring this down. 3 goes into 8 2 times. 3 times 2 is 6. Does 3 go into 2? No, right? It doesn't go into there. This is my remainder, right? This is my remainder. As is this. This is my remainder right here. It is my remainder. Now, if we were doing just normal long division, we would do something with the remainder. Since we're doing this for the sole purpose of a slant or oblique asymptote, the remainder doesn't really matter. I know, I just hurt its feelings. I'm so sorry, remainder. I don't want to hurt your feelings, but you don't really matter. I said that again, sorry. We don't deal with the remainder at all. So then what is my slant asymptote? Okay, so we're going to go back and we're going to look at this part right here. That is my slant asymptote, the thing that I just outlined in green. It's y equals 3x plus 3. That is the equation of my slant asymptote. Y equals 3x plus 3. Wasn't that fun? Okay. I'll try to calm down. Sorry. All right. How are we on oblique asymptotes or slant? Who knew you'd be having so much fun today? Right? Okay. Last one. Let's look and see what's happening. I've got a squared, that's my degree of my numerator, and a squared. They match. What am I going to have? Am I going to have a slant or a horizontal? I'm going to have a horizontal. It's going to be a horizontal asymptote. And how, if they match, how do I find the horizontal asymptote? What do I do? Yep, I take these coefficients and I divide them. That's what I do. I just divide them. So it's going to be y equals 8 over 4, which simplifies to y equals 2. So I have a horizontal asymptote at y equals 2. We wish they're all horizontal asymptotes, right? No, then we wouldn't get to have the fun with long division. All right, so one little note. It's impossible to have both a horizontal and a slant asymptote in the same equation. Impossible. You're going to have one or the other. It's either going to be horizontal or it's going to be oblique slant. Never both. Okay? All right.